fellow mathematicians. Welcome to the podcast where math is figure-outable. I'm Pam.
And I'm Kim.
And we're here to suggest that mathematizing is not about mimicking or rote memorizing, but it's about thinking and reasoning, about creating and using mental mathematical relationships. That math class can be less like it has been for so many of us and more like mathematicians working together. We answer the question, if you're not teaching algorithms, then what? All right, y'all, in the last episode 31, we talked about the over multiplication strategy. And we also talked about strategies in general and why we emphasize helping students develop strategies instead of spending all that time getting down the steps of the algorithm. Because let's be clear, it takes a while to get those steps sort of ingrained in kids' heads and getting them successful. Most students take quite a while. We practice over and over to get them to be able to do that. Instead of taking all that time, what if we put that time into actually helping build the relationships in students' heads so they can think and reason more and more sophisticatedly? So check that episode out. Episode, what did I say? 31.
Yeah.
If you want to know more background and you want to know more about the over strategy.
So in today's episode, I'm super excited because we want to highlight one of my personal, very favorite multiplication strategies. It's so slick and maybe one that not everyone makes use of, but we wanted to work with it today so that you can all have access to it.
Yeah, so to start off, let's be clear that this is a mathy episode. So you might want to grab a pencil if you're Kim or a pen if you're me, and maybe a piece of paper and listen to it now. Or like if you're driving or whatever, go ahead and hang on to as much as you can, but drive carefully. But maybe keep track of some of the relationships. Drive careful, everyone. Okay.
Yeah, so I'm going to give Pam some problems to develop this strategy this time. Are you ready, Pam?
I'm ready.
Okay. So we're going to do a quick problem string, right? A series of problems to develop this strategy today. Here's your first problem. It is 16 times 3.
16 times 3. Okay, I don't just know 16 times 3. I actually know 16 times 4, and I know 16 times 2, but 16 times 3 is kind of in the middle, so it's not so much. So I'm going to think about 10 times 3 is 30, and 6 times 3 is 18, and 30 and 18 is 48. 16 times 3 is 48.
Cool. So your next problem is 8 times 6.
8 times 6. And that's just a most missed fact, but I deal with it a lot, so I just know that's 48. Hey. So hang on a second. You gave me 16 times 3 is 48. I'm going to be very verbal during this problem string. I'm going to try to say everything that's going on in my head. So you gave me 16 times 3, and I figured that out as 48. And then you gave me a problem with the same product. 8 times 6 is 48. So I'm thinking something's up.
All right. You ready?
Yeah, I'm looking. I'm thinking.
You writing these down?
I am, yeah.
That would be useful, yeah. So the next problem is 24 times 30.
24 times 30. I don't know that that's related to the other one. This is going to be much bigger. Okay, so I'll just go and figure it out. Let's see. I'm going to think about 24 times 30 by thinking about 24 times 3 and then scaling it up by 10.
Okay.
So 24 times 3 is like 3 20s is 60 plus 12 is 72. So I think 24 times 3 is 72. Scale that up times 10, that's 720.
Very nice.
Okay.
24 times 3 and then scale it by 10. Okay, you ready?
Mm-hmm.
Your next problem is 12 times 60.
12 times 60. I'm going to think about 12 times 6, which I'm pretty sure is 72. And let me tell you what I'm thinking in my head. I know that like multiples of 12, I never worked on multiples of 12. And so later in life, I've dealt with a lot of 12s. And so I know that 5 times 12 is 60. That one's just ingrained. And so when I was thinking about 12 times 6, I just really quick checked myself to think about 5 12s is 60. So 6 12s, sure enough, is 72. So if 6 12s is 72, then 60 12s is 720. Scale that up by 10. 700. Hey. Okay, so those of you that are driving and aren't writing this down, Kim had given me 24 times 30. That was 720. And now I just did 12 times 60. That's 720. And I am seeing a relationship. So let me back up. Kim gave me 6 times 3.
16 times 3. Yeah.
Thank you. 16 times 3 and 8 times 6. I was thinking about that. 8 times, that's 6. So 16 times 3 and 8 times 6 had the same product. 24 times 30 and 12 times 60 had the same product. So when I look at the relationships between those pairs of problems, there's definitely some doubles and halves happening here. So like 16 times 3 then became 8 times 6. 16, half of that is 8. 3, double that is 6. So that's interesting. So if I'm thinking about 3 16s, could I think about 6 8s instead? Because like 3 16s, I need 3 of those 16s. But 6, I think about double, I only need half as many. So I can think about 6 8s. Because I don't need 3, I don't need 6 16s, I only need 3 16s. So if I find 6 half as big of those things, then they should have the same product. I wonder if that holds. Let me think about this second one. So 24 times 30, that's like me needing 24 30s. And then the next problem you gave me was just half of that, 12. Well, if I need 24 30s, so if I'm only going to work with 12, then I need things that are twice as big. If I only finding half as many of them, I need to find the twice as big. Did I say? How would you do that, Kim? I don't know.
I need half as many that are twice as big.
There you go. Okay, yeah, I need half as many of things that are twice as big in order to have the same product.
Okay, Pam, I have a last problem for you. You're noticing some sort of pattern here, and I wonder if that would be useful for you when I give you this problem. It is 5.5 or 5.5 times 18.
Okay, so I need 5.5 18s or 18 5.5s. I'm going to sort of think about finding, instead of 18 5.5s, I'm going to find 9 of things that are twice as big, because 5.5 times 2 is just 11. So instead of finding 18 5.5s, I'm going to find 9 11s, right? Yeah. 9 times 11 is 99. Bam! Woo! What
so nice.
Nicely done. Yeah. Good string, Kim. I like it.
Thank you.
So this is an interesting strategy, right? This idea that if I need to find, like we just said, 18 5.5, so that I can find half as many things that are twice as big. I bet we could look at this as area as well.
Sure.
In fact, on my paper right now, I'm drawing a 16 by 3 rectangle. So if I need the area of a 16 by 3 rectangle, I think I could cut that rectangle in half. So now I have an 8 by 3 and an 8 by 3, and I'm just going to think about that 8 by 3 tucked up next to that other 8 by 3. And so now I have not a 16 by 3, but I have 2 8 by 3s next to each other. That's like an 8 by 6. And I didn't lose any area. So we could think about kind of ripping a rectangle in half and moving the area around, actually using the associative property. You reassociate that area, and voila, we have a new rectangle, but with the same area. So that would be a way to kind of have a proof without words, that we could sort of like shift area around to kind of think about why we can do this double one factor and half the other factor, and the product stays the same because we are doubling one dimension as we half the other dimension, and the area stays the same. Very cool.
Yeah.
All right, so we call this doubling and halving. That's the doubling and halving strategy. Very cool. Let's do a couple problems to sort of demonstrate how this could be useful. So, Kim, here you go.
Yep.
35 times 18.
Ooh.
Do it.
35 times 18. So since we're talking about doubling and halving, that's kind of on the forefront of my mind. And I'm going to think about this like, I don't like 35 times 18. So I'm going to double 35. And since I doubled that dimension, I'm going to halve the other dimension. So instead of 35 times 18, I've created a new problem that is 70 times 9.
Because double 35, sorry, I'm slowing you down. Double 35 is 70, and half of 18 is 9. So 70 times 9, okay?
Yep. And so since I'm since I'm solving the problem 70 times 9, I know 7 times 9 is 63. And I'm making it 10 times bigger, or it is 10 times bigger. So 7 times 9 is 63. 70 times 9 is 630. 630.
So you scale it by 10. Nicely done. That's a good application of doubling and halving. All right, give me one.
All right, ready? Let's go with 25 times 64.
25 times 64. Okay, so I'm going to double the 25 to get 50 and halve the 64. Half of 64 is 32. And you know what? I'm not satisfied. I think I can continue to go. So I'm going to double the 50 to 100. Woo! And halve the 32 to 16. And now I have the equivalent problem 100 times 16, which is just 1600. And I just solved 25 times 64 in
Nice.
a couple of doubling and halving steps. Yes!
Yeah, and actually you doubled, right? And we know
And have halved, right?
and
Double,
have
double,
halved.
halved. Uh-huh.
So we know that doubling and having twice is the same as quadrupling and quartering.
You're going to go there, huh?
I
Okay.
am.
All right. All right.
Yep.
So you're saying that we could also quadruple the one length of a rectangle and quarter the other one, and we wouldn't lose any area.
Right. Which is part of why we don't love this name double half, right?
Yeah, totally. Because we could double half, we can triple third, we can quadruple quarter.
Yep.
We could, like, as long as we maintain the same factor, that we multiply one factor by a number, that we divide the other factor by that same number, by that same scalar, then we've kept the product the same. So yeah, we don't love the name doubling halving, but it's all we have to go with right now. So we're gonna go with it. Okay,
all right,
cool.
Give me one.
Okay, let's see. How about a problem like, hey, in our last episode, you might have noticed that Kim gave me a decimal multiplication problem. So back at you. How about 14 times 2.5?
14 times 2.5. Oh, that one's not so bad. Thanks for that. So I know that 2.5 times 4 is just 10.
Whoa, that's
kind of
fast.
10. I love 10. So 2.4 times 2.5 times 4 is 10. And since I quadrupled one of the dimensions, then I'm going to quarter or divide by 4 the other dimension. And actually, I happen to know this one, but if I didn't know, I could just have.
If you didn't know, 14 divided by 4, right?
Yeah.
That's what we're
doing.
So
14 divided by 2 one time is 7. And then divided by 2 again is 3.5. So 14 times 2.5 is equivalent to 3.5 times 10. And it's interesting because I still have decimals in my problem, but I would so much rather do 3.5 times 10 because that's just 35.
Yeah, I just scale it up by 10. Nice, nice. So now the original problem, 14 times 2.5 is just 35 with a little quadrupling and quartering.
Yeah.
Or like you said, you could have double halved and then double halved again.
Right.
Either way. Yeah, cool. So one of the nice things is to recognize, it's funny because when I gave you 14 times 2.5, you were like, oh, that's not too bad. But I think that's because you've doubled a lot. And so you know this relationship between 2.5 and 10.
Yeah.
Whereas for sure, when I started my journey to numeracy, I didn't. I had no idea that 2.5 doubled was 5 and 5 doubled was 10. So there's this beautiful relationship between 2.5 and 10. So much so that now I play around all the time with 1.25, because 1.25 doubled is 2.5. And now we're at that 2.5 landmark place again. So 1.25 or 1/2500, 1.25 is also brilliant to think about this doubling and halving strategy, because I know it can scale up to 10 so easily. So that's kind of a cool relationship. Okay, cool. So we could generalize this strategy to not just doubling and halving, but tripling and thirding. That is so not a word. Multiply by 3, divide by 3, quadrupling and quartering. And then after that, I think we have to sort of generalize: multiply by 5, divide by 5, multiply by 6, divide by 6. Like whatever it is, as long as we maintain that sort of same scale factor, it's multiplied by the factor and then the other is divided by the factor, then we maintain this equivalence. And that's really a cool part of this strategy. Kim, can I just tell you where I first sort of ran into this strategy?
Sure.
So I didn't say that very well. I first ran into it. I'm reading Kathy Fosno's work and thinking about alternative strategies. But then I was doing some numeracy work and a friend of mine in her high school classroom. So Abby Sanchez teaches high school.
Yay.
She used to teach just down the road from me. And I was doing some numeracy work with her Algebra 1 students. And one day, as I was doing totally a different strategy, this kid raised his hand. He was kind of this snarky kid. He was like everybody. He was the kind of kid like everybody kind of joked around with, and they liked him. You could tell because he kind of had this really like kind of almost Kim attitude towards the world. and he looked at me and he goes, "Hey, is that why that works?" And I was like, "Is that why what works?" Because we were doing something totally different. And he goes, why you can double one number and divide the other one by 2, and you get the answer. And kind of said it kind of like, like kind of like a freshman snarky kid would say it. And I was like, oh my gosh, there are kids out there that have developed
Mhm.
doubling and having
Mhm.
on their own. He's like, well, yeah, it works. But is that why it works? Like, he was really clear it worked. He just wanted to get kind of behind the scenes about why it worked. So right then and there, we kind of dove in and explored a little bit the doubling and having strategy. It was a lot of fun.
That's cool. That's really
So,
cool.
Kim, when you run into a problem and you decide you're going to double and halve, how do you decide which number to double and which to halve?
Oh, people ask us that, right? And they
Yeah.
ask about how do you teach your kids? I'm air quoting. How do I teach my kids to know which one's which? And there are some generalizations that we kind of want kids to develop, but that's the word. We want them to develop that idea, right? We
Mhm.
have got to let kids mess around to come to their own conclusions about would you want to have evens or have the odds, the idea that you often might want to try to get out of fractional parts or decimals. And if I may, with a story real quick,
Mhm.
I was so happy when doubling and having became part of my youngest son Cooper's repertoire. He now double halves so often, but I've never had a direct instruction with him. In fact, I don't know that I've ever done a problem string with him, and I'm not sure that he has at school yet. But he's heard me and my oldest son talk a little bit about messing with numbers, and this is why we would
Nice.
advocate so much for just talk about what you think about.
Yeah, just be
Um,
verbal, right? Just talk. It's one of the reasons why I kind of tried to think out loud as I was solving the problems today, is to kind of model what it means to say what's kind of going on in your head.
yeah,
Okay, sorry,
yeah.
sorry to
No,
interrupt. Keep
no, it's
going.
okay. And so it has become part of one of Cooper's strategies, and
So
it
cool.
is so fun to see him mess with numbers. And now, pretty often when he's doing, like a math assignment, or especially when we're doing math strat chat, I will do a particular strategy, and he's kind of snarky like me, and he'll say, why didn't you double half?" And it'll not be what I'm thinking about, or I'll miss it sometimes. So we want to encourage you guys to be on the lookout. If doubling and having or tripling and thirding is something that you haven't ever thought about before as a
Hmm.
multiplication strategy, or it's something that you find that you don't use very often, maybe make a note, or try to keep it on the forefront of your mind, because there are so many great opportunities to use this strategy.
Absolutely. Like, tell your math friends or even tell your students, like, hey guys, with this great strategy, I'm trying to use it more often. Help me recognize when it would be a good time, when I'm just sort of missing that it's an opportunity. I could
Yeah.
bring those relationships to bear. So, one other small note, Kim mentioned earlier that we don't want to direct teach this strategy. We're not
Yeah.
advocating that you stand up. I'm going to tell a quick story. No names, no names. Just so you know, Kim and I will. Tell you what, we'll tell you what we think, but if it's negative, we'll never give a name. Like, your name is
Sure.
safe with
Yeah.
us. So real quick, we just tell a quick story with no names attached. Quite a while ago, we were doing some filming of problem strings. We had some teachers that volunteered. They're like, yeah, you come in our classroom and video me giving a problem string. And so we had, I don't know, 5 or 6 teachers. Kim was one of them, another teacher in the district. And so I walked in the door, and these were real low tech. It was just me holding a camera. And I walked in the door and I said, okay, you ready? All right, I'll just be in the back. And I held up the camera, and she stood at the front of the class and she said, all right, today, guys, today we're going to learn the doubling and having strategy. Here's what you do. Step 1, step 2. And she had literally broken down the strategy into steps. It's like she had the Z perspective, that math is
Hmm.
all about procedures and mimicking someone's steps. And she just couldn't like get out of that. And so she, all right, here are the steps. And she said, so for the first step is you double the first factor, and then the second. And so everybody do that. Here we go. She has a sample problem. Everybody do that. She said, and then you half the second factor and see, and then now see, it's an easier problem. And so you solve that one, see how that worked. Okay, that was really cool. So that she did one, and then they did one together, and then she kind of assigned everybody to do another one. Kim, the hilarious part of the story for me, well, first of all, after a couple minutes, I was like, "Is she doing the non-example?" Like, I was in the back of the room
Hmm.
trying, like, "What are you doing?" Because I it was so clear that that's not what we're advocating, and somehow we just hadn't worked with her long enough or whatever. She couldn't quite get out of that perspective. But the funniest part of everything is, remember, she said the first step was to double the first number and have the second number, whereas you just a minute ago were saying we need to let kids fuss with that. We need to
Right.
let kids try. How do you decide which number to double and which one to have? Because you could do either one. So the problem that she had chosen to demonstrate was 12 times 24, or at least one like it. I don't exactly remember what it was. And listeners, you're like, what's wrong with that, Pam? Well, guys, let's follow her strategy real quick. So if her strategy is you have to double the first number, so double the 12 to get 24, and have the second number to get 12. Wait, wasn't that the same problem we had to start? So if the problem is 12 times 24 and you double and have in her lockstep fashion, you get 12 times 24 turning into 24 times 12. And then she kept going. Then she got 48 times 6 and etc. So interesting, right? Like she was so not catching the vision that it's not about I'm going to force the strategy on the numbers no matter what. You're still thinking. It's not about memorizing strategies. It's about thinking and letting the relationships influence the strategy that you're going to use. All right, cool. So a little bit of story there. So we don't love the name. We said that before. If you can think of a better name for this strategy, tweet or post about it. We would love to hear your suggestions for a better name for this strategy. We didn't come up with doubling and halving. That's been out there for a little while. It totally represents well, describes well the relationships you use if all you do is double and half.
Right.
But what about if you half and double, or what all the other factors, like we said, quadrupling and quartering and all the rest of them. So we want it to sound good, not too technical, not too jargony, also not too informal. Like it can't be Mary's strategy or what's the lasso strategy. Like it can't be goofy. I don't know. I'm looking around my office to think of the light switch strategy. Like it has to be mathematical enough that it would work great when if a teacher says, what are you doing? And the student said, I'm using this strategy. The teacher could sort of mathematically hang on to what's happening. Because one other, I'm making it really, like you have to find a good name that meets all these criteria. Another criteria is that when students are first learning it has to make sense. Because I've had some people suggest some strategy names that make sense when later I want to generalize it to all the things. But it also has to sort of make sense in the beginning when we're calling it doubling and halving, or in the beginning when all we're doing is doubling and halving. But later it feels general enough so that when students want to scale by the scale factor and then divide by that same scale factor, or in middle school, instead of dividing by that factor, you multiply by 1 divided by that scale factor. Either way, so we want it to be recognizable to the beginning student, but also scalable so that it works kind of when we get more general. So if you can think of one, we would love for you to tweet about it, post it on Facebook or Instagram with the hashtag #MathIsFigureOutable, and we will check those out.
Absolutely. Hey, there's problems all over the world, but if you are looking for an opportunity to try out the doubling and halving strategy, remember to join us on Math Strat Chat on Facebook, Twitter, and Instagram on Wednesday evenings, where we explore problems with the world. And many of those problems, you would be able to use double and half.
Yeah, it'd be a great strategy to use. Or some version. Nice. And remember, we've created Math Strat Chat Central, where you can find all of the problems. If you can't find that, just Google Math Strat Chat Central, and maybe Pam Harris, but I don't think you even need that. It'll come right up where we list all the problems we've ever asked on Math Strat Chat. Click on it, and it'll pull up the Twitter feed where you can see strategies from around the world. So, if you're interested to learn more math and you want to help yourself and students develop as mathematicians, then don't miss the Math is Figureoutable podcast, because math is figureoutable.